In this video, we begin our look into Chapter 10, that is the chapter about gases. And so to start this chapter, let's kind of review a little bit about what makes gases so unique. Well, we know that gases do not have a definite shape or volume. We know that gases uniformly expand to fill any container that they get put into. We know that gases will exert pressure on their surroundings. We know that gases will change volume based upon temperature and pressure settings. We know that gases mix with other gases, and when they do so, they mix very uniformly, very completely. And we know that they have really low densities, whereas liquids and solids tend to have their densities measured in grams per milliliter. Gases tend to have their densities measured in grams per liter. Because they take up way more space. They have way larger volumes per mass, so they're way less dense. Now, when it comes to describing gases, we can often talk about gases in terms of their parameters. And what we mean by parameter is some sort of measurable quantity that we can use to describe the gas itself. And so in particular, we talk about four different parameters surrounding gases. We can talk about a gas's pressure. We can talk about a gas's volume. We can talk about a gas's temperature. And we can talk about the number of moles of gas that are present. Now, all four of these parameters can be described and have interactions with each other through what we call gas laws. And we'll talk more about the gas laws and some of the things that they quantify in a later video. But for right now, we're going to look at things primarily from the standpoint of qualitative kinds of descriptions, things that don't require numbers, and we can talk more about conceptual relationships. And for that, we need to use something called the kinetic molecular theory. The kinetic molecular theory is an explanation of most of the gas's behavior through a series of assumptions. So what are those assumptions? Well, first of all, we assume that gas molecules have tiny volumes compared to the volume of their container. So when we describe the volume of a gas, we don't really talk about the gas particles themselves. We just talk about how big the container is that they're in. We can also talk about gas molecules in terms of, because of their distance, because of the how far apart they are from each other, we don't typically think of gases as having intermolecular forces. They don't tend to interact with one another. We know that gases are in constant random motion. And so they move around their container, they move around randomly, they move around constantly, and occasionally they interact with each other. So when they interact with each other, or when they interact with the walls of their container, we assume that they interact with elastic collisions. Now, elastic collisions, what we mean by those is that the collision has no net energy loss associated with it. So all of the energy that goes into the collision comes out of the collision. And so there might be energy transfers that occur. If I have a gas molecule that is moving quickly and one that is not moving very much at all, the faster moving molecule may donate some of its energy to the slower moving molecule and help the two reach kind of a energetic equilibrium. But there's no net energy lost overall in these collisions. And the last assumption that we make is that the gases have an average kinetic energy that is directly proportional to their absolute temperature. And we've talked about this relationship in another number of different ways before. The relationship between temperature and kinetic energy plays very much into the role of why we have a Kelvin scale in the first place and what absolute zero is. So these are our fundamental assumptions of the kinetic molecular theory. And looking at each of these five, you look at them and say, well, okay, none of these are really all that earth-shattering. In fact, they make a lot of sense. So the real question is, how do we use the kinetic molecular theory? What can we do to actually try to rationalize relationships between parameters or make some more fundamental assumptions as a result of it? So let's go into this next concept. And for that, I'm going to pose a question to you that I'm going to give you a couple of seconds to think about. Keeping in mind the ideas of the kinetic molecular theory, what is the relationship between the mass of a gas and how fast that gas moves? So take a second, pause this video, and try to sketch out a couple of ideas for what this relationship could be. And if you haven't paused yet, please do so. Otherwise, we're going to move over in 3, 2, 1. So the answer here lies into the idea of kinetic energy. We know, according to the kinetic molecular theory, that if we are at the same temperature, then the molecules of the gas must have the same kinetic energy, or at least the same average kinetic energy. And so, with in mind our equation for kinetic energy is 1/2 mass times velocity squared. And so, if all of our kinetic energy is the same at a given temperature, if our mass is high, then our velocity has to be slower to account for that. And so what we can see is this is a graph of different particle speeds, average particle speeds for different types of gases. And what we can see is that the lightest gases, hydrogen, have a faster average speed overall than the heavier gases like nitrogen and oxygen, which have a considerably slower speed. And the relationship is a root mean square relationship, meaning there is going to be a relationship between the square of the velocity and the mass, not just the velocity and the mass. Now, we can quantify this and we can qualify this through a couple of concepts. One of those concepts is called effusion. Effusion is a relatively simple idea. Let's say I have a container of gas and I poke a small hole into that container. Such that the gas molecules in that container start to flow out of the box through that hole. That is what effusion is. Now, so effusion is I've got a hole in a box, I've got a hole in a container. How quickly do the gas molecules inside the container go through the hole to the outside of the container? Diffusion is slightly different. Diffusion is about the spread of gases or the spread of substances from one area to another. So from a gas perspective, we're talking about the spread of gas in all directions and how quickly that process happens. Easy way to think about this is let's imagine that you're at home, you're making cookies, and the cookies are in the oven and you're waiting for them to finish up, but you're in a different room and you can tell pretty quickly if the cookies start to burn because the bad smell of the smoke would diffuse from the oven where the cookies are on fire to the other parts of the house to let you know that something's not right. So that's diffusion, the spread of a gas in all directions going through an entire space. Now, we can quantify diffusion and effusion using something called Graham's law. Graham's law states that the relative rate of diffusion, or effusion, is inversely proportional to the square root of the molar mass. And so there are a number of different ways that we can look at it. We can look at relative rates of effusion, where we just take the time, how long does it take for one gas to effuse compared to another, and compare it directly to the square root of the ratio of the two molar masses. Now we can also look at this from a standpoint of distance as well. And from that standpoint of distance, if we're looking at how far will a gas diffuse in a set amount of time, we can do the same kind of calculation with the same kind of relationship. The only problem with this second equation is that it's actually backwards on this side. The distance is inversely proportional as opposed to the time. So time is going to be directly related to the square root. Slower gas, heavier gases move slower, take more time. Lighter gases take less time. Distance is going to be the reverse. It's going to be a lighter gas moves more of a distance and a heavier gas moves less of a distance. So let's take a look at a couple of examples. First example here is a purely qualitative example. Based upon the molar masses of these four gases, which order would they go in terms of increasing rate of diffusion? And so increasing rate of diffusion means that as we go from left to right, we are going to get faster. And so all we need to do is look at the molar masses of each of these and put them in the appropriate order. So helium is 4.003 grams per mole. Krypton is 83.80 grams per mole. Nitrogen monoxide is 30.01 grams per mole. And oxygen is 32 grams per mole. So the heaviest gas would be the slowest gas, so that's krypton. Krypton is slower than oxygen, which is the next slowest, which is slower than nitrogen monoxide, which is the next slowest, which is slower than helium, which is the fastest. So in qualitative examples like these, we don't actually need to do calculations. All we need to do is evaluate the molar mass and put them in the appropriate order. For the other type of example, now we look at what is the molar mass of, if we have equal volumes of oxygen and an unknown, and they take this long to effuse through a small hole. Now for that, we're going to need Graham's law. Graham's law says time 1 over time 2 is equal to the square root of mass 1 over mass 2. So if I put in my values, time 1, 3.25 minutes, time 2, 4.60 minutes, equals the square root of oxygen, which is 32, and our unknown, which we're just going to call x. And so for problems like this, easiest way to go about it is to square each side to get rid of the square root. If I do that, 3.25 divided by 4.60, quantity squared is 0.499. Units of minutes cancel there, is equal to 32.00 grams per mole divided by x. Doing some last minute algebra, x is equal to 64.00 grams per mole. So that's how you can do some quantitative Graham's law kinds of problems. In the next video for today, we'll look at pressure and pressure units, and that'll lead us into gas laws. Have a good day.